Hi, my name is Coprocessor. I'm the Principal HPC Research Engineer at Colfax International, and I welcome you to our video course Parallel Programming and Optimization with Intel Xeon Phi coprocessors. In this video episode 2.1, I will introduce Intel Xeon Phi coprocessors based on the Intel Many Integrated Core or MIC architecture, and will cover some of the specifics of hardware implementation.
Intel MIC architecture is a highly parallel, energy-efficient processor architecture that achieves high performance through utilization of a large number of cores, wide vector registers, and high bandwidth on packaged memory. Intel Xeon Phi coprocessor is the brand name of computing accelerators based on the Intel MIC architecture, and so those two names will be used interchangeably in our training course. The current generation of Intel Xeon Phi coprocessors is based on a cheap codename Knight's Corner, or KNC, and we will also occasionally use this name to refer to Intel Xeon Phi coprocessors. The next generation of Intel MIC architecture will be based on the Knight's Landing Chip, or KNL. It will be available not only as a coprocessor, but also as a standalone processor. Xeon Phi coprocessors are PCI Express endpoint devices. They are primarily used for offload of performance-critical parts of an application and for heterogeneous clustering. For highly parallel applications, Xeon Phi coprocessors had theoretical peak performance up to 1.2 teraflops per second in double precision and 2.4 teraflops per second peak performance in single precision. The theoretical peak bandwidth of the onboard memory is up to 384 GB per second. However, in practice, we observed about 160-180 GB per second. Connectivity with the host system is provided by a BY16 PCI Express Gen 2 interconnect. Compared to the multi-core Xeon processor, Xeon Phi coprocessor delivers better performance per watt because its cores are more simple than Xeon cores. Xeon Phi can also yield better performance per unit of rack space because you can put multiple coprocessors in each compute node. This graph produced by Intel is a benchmark test of a high-performance lean-pack benchmark, linear algebra type of workload. In this particular benchmark, as well as in most other benchmarks presented in this video course, we compare a two-way E5 series Intel Xeon CPU with a single Intel Xeon Phi coprocessor. The reason we compare two CPU sockets against one Xeon Phi coprocessor is because the thermal design power, or TDP, of two Xeon processors is about the same as that of one Xeon Phi coprocessor, between 225 and 300 watts. The graph shows us that Xeon Phi performs 3 times faster than two Intel Sandy Bridge processors and 2 times faster than two Intel Ivy Bridge processors. Next, let's compare those two architectures side by side in further detail. The key common feature is that both Xeon and Xeon Phi can run applications compiled from the same source code. That applies to languages, parallel frameworks, and most importantly, performance optimization methods. Those are common for multi-core CPUs and many-core Xeon Phi coprocessors. C, C++, and Fortran programming languages are supported by both architectures. Standard parallelization frameworks such as OpenMP library and MPI are supported by both as well. The reason why this is possible is that Xeon Phi coprocessors run a full Linux operating system called MuOS. This operating system is loaded by the coprocessor driver on boot. The continuity of optimization methods is due to similar architecture of processors and coprocessors. Xeon processors have direct access to a large amount of DDR memory, up to 768 GB per socket, and this memory is cached. Similarly, Xeon Phi coprocessors have access to a 6, 8, or 16 GB of cached GDDR5 memory. However, they cannot directly access the host memory. We'll discuss this later. Xeon processors have anywhere between 2 and 18 cores per socket, each operating at around 3 GHz frequency, whereas Xeon Phi coprocessors have between 57 and 61 cores, clocked between 1 and 1.2 GHz. Xeon processors have two-way hyperthreading, while Xeon Phi coprocessors have four-way hardware threading. Finally, both Xeon and Xeon Phi can perform vector operations in each core. Vector instructions supported in Xeon CPUs are 8 wide in single precision, and Xeon Phi vectors are 16 wide. We will discuss vectorization in great detail later in this course. Let us take a look at a case study which compares two architectures using simple n-body simulation. The key element here is that the same exact C code is benchmarked on the two architectures and even scaled across multiple coprocessors. In our simplified implementation, 40,000 particles interact gravitationally with each other, and thus the algorithm complexity is O(n)². We first benchmarked the simulation on two Intel Xeon CPUs. With Xeon processors, the performance is about 6 steps per second. Next, we ran the same exact performance-critical code on one Xeon Phi coprocessor. We used explicit flow programming model for this. Compared to the Xeon processors, we observed a 4x speedup. Coordinates and velocities of the particles are synchronized on every iteration. Finally, we ran the simulation on two Intel Xeon Phi coprocessors. Particles are split into two groups and processed synchronously by two coprocessors with a full update of the system on every step. We observe a speedup that is close to the theoretical 2 times speedup, linear scaling, and almost 7.5 the performance of two Xeon CPUs. The main takeaway from this video is that with proper optimizations you can expect significant improvement in performance by using Xeon Phi coprocessors with a single code base.
In the final minutes of this video, let me introduce you to the available models of Intel Xeon Phi coprocessors.
The Xeon Phi coprocessors came in performance shelves, the 3000 series, 5000 series, and 7000 series. The 3000 series has 57 cores and 6 GB of RAM. This is the price optimal performance shelf. The 5000 series has 60 cores with 8 GB of RAM at 225 watts TDP. This corresponds to the optimal performance per watt. The 7000 series has 61 cores with 16 GB of RAM, with theoretical maximum performance of 1.2 teraflops per second in double precision. This is the highest performance shelf. In the enumeration convention for Xeon Phi models, also pay attention to the second digit. This is the coprocessor generation. Currently, the only available generation is 1, which corresponds to the Knight's Corner chip. Finally, the letter after 4 numbers indicates the cooling solutions. Most people will need either passive cooling solution indicated by a letter P, or active cooling solution with a fan on board, letter A. What is important here is that the passive solution is only for servers, while the active solution may be used in workstations. Finally, here's 2 examples of system configurations built by Colfax International that utilize Intel Xeon Phi coprocessors. A workstation may be equipped with 1 or more active-cooled coprocessors, in some configurations up to 4 coprocessors. A server may be equipped with passively cooled coprocessors, and systems are available with 8 coprocessors per system as shown here. Those systems are available from Colfax International on xeonphi.com website.
In the next section, we will start the discussion of the details of the Intel mic architecture from the programmer's perspective, followed by an overview of vector instructions. Thank you for tuning in, and I hope to see you in the next episode.